Hello and welcome to another NX tutorial. In this tutorial, I want to compare the performance of different shaft cross sections. As you can see here, I have 4 different cross sections. I want to apply some torque on it while keeping the sizes of the shafts same, and then compare the stress and deformation on each shaft. Now basically I want to cut the cross section from the same size of the shaft. Here I use a 20 millimeter shaft, and then run a simulation by using a linear simulation and a linear contact. I will explain about that later. Only for the D shaft, you can cut different cross sections by changing T, but the best performance you get is from a D shaft where 20% of it is cut off. So the remaining T is equal to 80% of the diameter. So let's move to NX. I start by modeling the shafts first. Here I first make the main shaft, a 20 millimeter shaft, and then I need a reference line to replicate this shaft. I'm gonna use pattern and pattern this curve along this line. I have 4 shafts and click OK. First one I'm gonna do is the D shaft. Just need to make a cut here. Let me turn off this. And also let me yes, and I need to make a horizontal now. Okay. Now it is horizontal, and then I need to have a dimension here from, now I need to have a dimension from here to this point. This should be 0.8 multiplied 20 or 60. Now the shaft is ready and I can extrude. I'm going with region boundary curves, and I want to extrude 25 millimeters on this side, and then on the other side I need single curve. I just pick the circle, and 50 seems good. That's the other direction. I need to unite these two and click OK. So this is the shaft, and then I need to do the same thing for the hub. I start the hub from here. Let me turn back this on, and 50 seems good. And I also need to make the D section that is matching my shaft. I need to turn this off, and here we go. And I can actually trim off the subpart, so I don't need. And now I can extrude this. This I will extrude it for 20 millimeters and leave some gap here because I don't want these two faces to be in contact. This contact has no effect on the simulation, so I leave some space. Also, this sharp corner here is going to generate some wrong results, so I want to stay away from that. Now, speaking of sharp corners, here, before we move on, you need to remember that we need separate bodies, so we shouldn't unite here. Or you can just model the hub in a separate part and bring it to this as an assembly. But here I use none, the boolean, and now we get two bodies. So this is the hub body and the shaft body. Now starting from the shaft, let me hide the sketches. I have two sharp corners here that are going to make problems by making singularity. So I'm gonna generate fillet here and here. Sorry, this is chamfer. A edge blend. 0.5 millimeter is good. I will do the same for the hub. And now I can take this to the pre-post. I'm gonna save here. And go to the pre-post. Now before I make a new film and simulation file, I want to divide the face here on the hub so I can make a contact pair between the shaft and the hub. Otherwise, I have to make a contact between the whole face of the shaft, outside face of the shaft, and internal face of the hub, which makes the simulation slow. To do that, first hide the hub and I'm gonna use divide face. The face that I want to divide is basically all the faces I can select, and then offset the curve. I'm gonna offset these curves, and this line here shows where it is cutting, and I'm gonna go with 20, which is the size of the hub. And okay, so now we have a cut here. And let me bring back the hub. Yes, now we can see that I have a cut where the hub is sitting. Now this is ready for film and simulation file. So make a new film and simulation file. I want all the bodies in the simulation. Click OK. Here in the simulation, I want to do a linear static, but you need to know that contact in nature is nonlinear. So usually you need to go with 402 multi-step nonlinear or 106 or 601 for advanced nonlinear statics. But only if the deformation are small, you can use a static analysis and linear statics and linear contact. Now, to make that more clear, I'm going to show this example from NX user manual. As you can see here, we have a wedge that is moving in this direction, and these faces are going to be in contact with the top faces and bottom faces. In a linear simulation, the software is reading the geometries only once in the start of the simulation, and it will assume that faces are going to touch the faces in front of them that have the normals are facing each other. So the software will assume that this point P0 will touch the outside face at this point, and other faces are also touching like this. But in reality, the wedge is moving this way. So this point P will touch here in reality on point B. But a linear simulation or linear static does not consider large deformation like this much. The formations are small, so that's why in a linear contact, the software will sets this as the contact point. In a non-linear simulation, the software actually regenerates the contact faces. So this face will move here. There is now a new pair of contacts. The software is looking on that and it's going to be in this point. Then the wedge moves a little bit forward to this point and the software generates a new contact pair from this point to that point. And at the end, when the face is reaching here, the contact is generating the last contact pair at this point. So you need to make sure that the formations are small, otherwise you cannot use the linear statics. Here I assume that the formations are small and I can use the one-on-one linear statics. I create a solution, and before moving on, we can also change this in the solution and edit solution option. I want to request more output, so I will change this. Note that here you can request any kind of output that you want from the software. It will show up in the result. Here I only want to turn on the contact result so I can see contact pressure and contact force. Click OK and it will make a new solution. So here we are in the .fem file and we can start meshing. We'll use 3D tetrahedral and select all the faces. I reduce the size to 4. Let's see how it looks. Now let me hide the hub so we can have a better view of the shaft. Also with the polygon. Now here the problem is that I have a sharp corner on the fillet which may generate some singularities. So I need to make the mesh a little bit finer and the fillets. To do that, we can use mesh control and these faces. And we can use fillet option and pick these two fillets. The sizes are okay. And I'm gonna do the same thing on the hub. Doesn't matter if you pick the polygon or the mesh. Here I have a fillet here and one here. Use the same size and update the mesh. Now if I bring back the mesh and hide the polygons, let's take a look at the shaft. Now you see that I have a bit of a finer mesh along the fillets, except this end, which I'm not going to look at the result. If we take a closer look, now we have two elements along the fillet. So this is, the mesh is ready now and I can apply the constraints. Let me hide the mesh and bring back the polygons. I'm going to save here. Before I move, I can also define the material. Here I'm going to use aluminum and okay. Let's go to the simulation file. Now the first thing I want to do here is to make surface-to-surface contact. Here I go with automatic pairing and select all the faces and click OK. And I want to, here you can see that we have 4 pairs, which is with the face that we made and the face of the hub, plus the fillets, the top face and the other fillets. It's going to be 4 faces. I also want to add some friction and click OK. Now if I hide one of the bodies, here you can see the arrow that shows the contact face. Here we also have an opposite arrow from the hub. So the contact is set. Now I can set the constraints. First I want to fix the hub, only the outer side of the hub. And for the shaft, I only need to fix the Z transition. The rest will be handled by the friction and contact. So I'm going to define a user-defined constraint, and it's enough to only define it on this point. And I want to fix all the degrees of freedom except the Z movement. So these DOFs from top means XYZ transition and then XYZ rotation. So I'm fixing, and this is the vector or coordinate that we are using. So I'm fixing the Z transition. So I need to free everything and fix the Z transition. Now you also see it that with a cross on the Z direction. And last is the load. I want to add a torque on the shaft, and we need to use the same amount of torque on all shafts. So I'll go with 1000, or let's go with 10 Newton meters. And click OK. I save here and I can solve the problem. Now the simulation is completed and I can take a look at the results. Here, go to results, and first I want to see the deformation result. Now here is of course exaggerated. It's scaled up by 10% of the model. This is the absolute deformation, but this is not what we expected actually. You see that the shaft is actually squeezed to the top of the hub, even though the maximum deformation is really a small hundredth of a millimeter. But the behavior is not what we expected. If I play the animation, you see that the shaft is actually moving up and pushes to the wall of the hub. Now let me explain what's happening here from the user manual, which is pointing out this problem actually. Here it says that because of the changes in geometry that are not reflecting into the mesh, they result in bumps or kinks. These are the problems with the initial penetrations. Let me go back to the mesh. Here I can explain what's going on easier. On the geometry, we have 2 geometries that are matching perfectly. But if you look at the mesh, let me bring back the mesh. At these points, for example, I have an initial gap, and at these points, I have an initial penetration. These penetrations that you see here, they will have an initial pressure toward up side of the shaft, and it's going to generate a distribution of pressure along the shaft, which is squeezing the shaft to the top. So this is also mentioned in the engineering analysis with NX Advanced Simulation, which I really recommend to take a look if you want to work with contacts. Here as well, it is mentioned that if you have curved faces, the mesh will not reflect the geometry perfectly, and you're always gonna have some initial gaps and initial penetration. Now it is mentioned here that you can easily fix that by changing the contact options. Here I go back to simulation objects, face contact, and we can set some extra options in linear contact or BCT parameter. Here on the initial penetration, you have different options. You can set the penetrations to 0 or both gaps and penetration to 0, which is very good for simulations where you have an initial touching faces like the way we have here. So I set both gaps and penetrations to 0 from the start. I click OK. There are also more recommendations here, both on the manual and on this book, which, for example, this here, it is recommended that if you have uh, some contact faces, multiple contact faces along the cut, it's better to define separate contact regions, except defining only one contact face. So here, what I can do is to go back and define manual contacts between separate faces. So let's go back and bring the polygons back. I will hide the mesh. I will start by removing this contact and then surface to surface contact. I go with manual. Now I have to define regions. The first region I want to have is this top face. And I want the contact between this top face and the bottom face of the hub. So let me hide the shaft. This is the face. I want friction as well and click OK. Now you can see that, so I have to fix that region. So let me first hide the constraint, and then I need to go back and also I'm going to remove all the regions. So I remake the regions and contacts again. First, let's just start from the top face of the shaft. The first region is this. And then the target region is here. Add friction and apply. The second region will be the fillets. So I go with this region. I can also add this region. And on the target, I have the same regions on the shaft. I select this and this fillet. Add friction and apply. And the remaining one is this region is source, and then same region on the hub. Add friction and OK. Now here you can see the vectors pointing out as contact. And now if you check the simulation objects, you will see 3 contacts, different contacts. Now here you don't need to go into each contact set and then set initial penetration and gap to 0. But we can't do this on the solution. I'll edit the solution. Here we have global contact parameters. This will override any contact parameters. So if I do it here, it will override all the options. Here I can change the calculate from geometry to set gaps and penetrations to 0, and that will uh, change all the contacts. I'll also check if the output is still has the contact result, which is correct, and OK. Now I solve it for the second time, and let's see the result. The simulation is now completed. Let's go and check the results. Our first thing we see here is the deformation or displacement. You see some kind of expand in the shaft, which is normal as the shaft is turning. If I play, see that the shaft is turning and expanding as the torsion being distributed to the shaft. And looking on the other side, we see that the contact is now behaving correctly. One corner is pushing the hub up and the other side is being pushed down. Now this is exaggerated, and we can take a look on the absolute deformation, which is really small. As you can see, it's not even visible here. I have to zoom a lot so we can see the real result. Now this result is actually very important because if we have a plastic region here, this deformation is going to be your backlash. This will generate a gap as the shaft is deforming the hub, and that will generate a backlash. Then that's why deconnection will deconnection is not good for applications that you don't want to have backlash, unless you have a screw that is holding a stud screw that is holding the flat side down. Now we can take a look at rotation, which we don't have per element here. Stress is very important here. We don't have failure since this is aluminum and the yield stress is more than 91, but it's good to check where are the stress points. I can hide the hub, and we can see as expected we have some stresses around here which we need to ignore actually because these are due to singularity, but we need to look here. So this is the stress we're looking for, and you can actually pick a point and see that this is 16.9, the stress on the corner. And also I can turn on the annotations so it will show automatically the maximum and minimum stresses. And then the nodal stresses will get higher results because we have higher stress on the nodes because the elements are some kind of average stress. Then we have contact. The important one is the contact pressure. So let's see what do we have and where do we have contact. If I play the animation, we see how the contact is changing along the face of the shaft from top and bottom. Also, let's take a look on the contact force. We see here how the contact is changing. I can turn back on the hub. It will only show the contact faces here. If I play, we can see how the pressure of contact is distributed in a D connection. Now here in the result, I want to check for the average stress and deflection. For the average stress, I go back to elemental stress. I'm going to consider only the shaft and assume that same amount of stress will happen on the hub. And let me return to the absolutes. I'm going to skip the sharp edge and pick the result of a box here. Can add more to make it more smooth. Average. So here I have average of 9.88 as average stress. Now for the displacement, I'm gonna go with the displacement magnitude, and then I will measure the deflection of one of the corners. If you look at the 10% of modal deformation, if I play it, here the deformation here is what I'm looking for because this is effective on the structural design of the shaft. We basically need a shaft that has less deformation inside the hub. So I will go to the absolute and then pick up a point in the corner, this point, and we have maximum. I'm gonna pick, and we can check actually if we have we pick the maximums. We can average all these 3 points. So the average is also almost the same. So I will write the deflection here, and I can here write D section. Now I have the D, and I can have the different cross sections that I showed here. I had hexagon and is a square. So I need to complete all the average stresses and deflections, and then we can compare.